So welcome back to section number 3 of linear algebra, honors for linear algebra. So in this section, I want to talk a little bit about how I solve these problems using my program. So what you want to do is you got your points. If you click here, the program will start running. And then what you do is that you come here, and let's say we got the x points, right, which are right here, 1, 2, 3, 4, 5. The catch here though is that you do have to put the brackets, otherwise the program won't work. And then our y value is 1.8, 2.7, 3.4, and 3.8. Oh wait, 3.8 and 3.9. And then if we run it, we should get this same question, which is the one that is right here. So you may see it right here. And then we get our beta values and we get our formula. So this gives us values as fractions. I did simplify them to write them as formulas, and then this is our final answer. And we get the r squared value. This program, the only thing that doesn't have that it was in the previous program was that the call A that is not here, because I didn't want to include it since most of the programs that I found didn't have beta enough value. But if you wanted to include it, you had to do the same thing as the last program. Put the call one here, and then you gotta include it under equation 2. And finally, so I showed up in the graph, you gotta include it right here. Not forgetting that for the values of beta, you gotta write rep, so I convert it into fractions. But there's another topic. Cubic functions are pretty much the same as this one. Use an extra variable, and then it does this same thing. We get the r squared value. We get the formula. So this is beta values or y formula now simplified, not fraction form, and then our r squared. So the only so I did two other programs, which are the sine cosine sort of function, which is in this form. This one works similar to this one. Just change the model, like the model is different, and it gave us this program. It gave us the beta values of a and b, which is the original formula. We'll get them as 7.48, which is b sine x, and then 2.342, which is cosine x. This one is actually pretty accurate too. It's 0.94. And then the last program I did was this one was exponential problem. So originally on my exponential type of problems, I wanted to be on the form of a e to the power of let's say bt, for example, which is the normal exponential formula. But the problem with it was that we get, apart from the a value, which you can get as normal, we needed to find our b value, which was a little bit more complicated. I found out that you can actually do a linear approximation of some of the exponential problems, but it's not as accurate as you may think, and it's just the problems that I couldn't find really much problems that deal with linear approximation of exponential problems, so I sort of skipped that part. And I work on two problems that have to do with growth factors. So you're given a growth factor, and then you had to find value of the constants, the initial amounts of concentrations, for example. So, for example, on this problem, they give you the growth factors, which are negative 0.2 and negative 0.7. I forgot to write the negative here. I'll add that on later on. And then you're asked to find the MA and the MB values, which are the initial values, and they are unknown. So they're telling you that they found they recorded how this changed, how the concentration changed in terms of time. So if you plug in your time concentration onto the program, which works a bit similar to other programs, the only thing that is added is that there's another input that um, that tells you to put your a values, your growth factors, a and b values. So that's the extra part on that one, but pretty much the other thing works the same. And then once you plug it in, so you see it generates this matrix similar as this, and so forth. So for this program, I got this type of line. This one was almost perfect. Like it was not that far from true. So as I say, a and b are defined in the program as the constant of decay. Well, I mean, on this type of programs are defined as constant decay, but on the programs are defined as the growth values. Uh, so yeah, like they ask you for the value of a and they ask you for the value of b, as I said before, and we've been going over the last section before the links for the program, and that will be it. So the last section talks about how to find the linear regression problems with least squared with calculus 3, which is multivariable calculus. So what you do is that you're given some points and you're given the question you want to model it, but you want to model your function. So what they say is that you want to minimize the square of the sum of these vectors of the vertical distance, my bad. So you want to minimize the square of the vertical distance between f of x and our data points. So what you do here is that you plug in, what you do is that you get your y value here, and you plug in your x value into f of x, and you follow like that with all the points you have. So for example, f of 0 is b, f of 1 is m plus b, and then f of 2 is 2m plus b. And then once you get here, you simplify and you get this formula: 1 minus b squared plus 1 minus b 1 minus m minus b squared plus 2 minus 2m minus b squared. And what you do from here is that you take a partial derivative. So the partial derivative in terms of m, it gives you this. Partial derivative in terms of b gives you this. If we simplify, I get these formulas: 10m plus 10b minus 10 and 6m plus 6b minus 8. And then right here we get a system of equations which we can solve actually in linear algebra just by row reducing. And we get our values, which are 1/2 and 5/6. And if we write a formula, we'll get that beta 1 is 1/2x and beta 2 is 6/5. And as I said before, so we try to minimize the vertical distance between our points and our functions, which linear algebra we actually express with a vector c. So we're pretty much doing the same as in linear algebra. So lastly, the last thing I want to show you is the link for the programs that I created. So here's a link. It'll send you to a Google Drive, or the folders for the program are zip. So you have to download the program, and that's it for my honors project. Thank you so much. Have a wonderful rest of your day.